All right, so we're going to be doing this problem right here, 4.100, out of Statics and Mechanics of Materials by Ferdinand. I think it's like second edition or something. Anyway, we've got this member right here, ABC, and it's attached to one continuous cable in two spots, and then it has an applied force. It looks a little bit complicated, more complicated than it actually is because of the cables right here and right here. And then this pulley. But when we look at the problem a little bit more deeply, that helps us decode it, and it makes it make a lot more sense. And so if we take a look at it, it says neglecting friction and the radius of the pulley. And so that means essentially these go straight to point D. Oh, geez, guys. Like that, and there's no radius, and then there's also no friction, because if there was friction, that would actually change the amount of force that's on both sides right there. And so we can start a free body diagram of member ABC just by drawing some force vectors coming out of both the points that the cable attaches to. And we're going to label these T, because another property of frictionless pulley is that, like I said, they're going to be the same on both sides. And so the same amount of force is in each of these, even though they're going to have a different angle with respect to that horizontal member. And so for this one, we're going to call it phi. This one, we're going to call it theta. And we're going to take these angles. We're going to figure out what they are, because we're going to need the vertical and the horizontal components of both of these to figure out the moment about point C, which we're going to take in just a moment. And so to find theta, we're going to use the tangent function. It's going to be opposite over adjacent. And so if we take the tangent of theta equals opposite over adjacent, that's going to be 150 millimeters divided by 200 millimeters. And so with that, theta equals tangent inverse of 150 over 200, which comes out to be 36.869 degrees. Now we're going to do the same thing for phi, but I'm going to skip this step right here and just do tangent inverse. And this time it's going to be 150 over 360 equals 22.619 degrees. So yeah, now we have both those angles. The next thing we're going to do is take the moment about point C. And then that's going to give us the ability to figure out what the force, the T, actually is in this problem, which is actually what the problem asks for. We didn't go over that yet, but it says tension in the cable and the reaction at C. And so right now we're going to find the tension in the cable. We're going to do that by taking the moment about point C, and this is a statics problem. Nothing's moving here. And so we're going to say the moment equals 0. And then we're going to say what that moment is. We have this force, the 120 newtons, that we have to deal with first. And so we're going to say 120 newtons times the distance, the horizontal distance from point C, which is 0.28 meters. Like that. And we're calling it positive because it would cause a counterclockwise rotation about the point, which, due to positive sign convention, is a positive moment. And then we're going to subtract, we're going to focus in on the cable at point B. We're going to subtract it. We're going to say T. And then this horizontal component right here doesn't do anything, right? It's pointing straight into the point that we're taking a moment about. And so we don't have to worry about that, but we do have to worry about this. And so to get that vertical component, we're going to use the sine function. And so we're going to say T, the force T, times sine of the angle, which in this case is 36.869. And so this is just the force right here. Because we're doing a moment, we also have to take that horizontal distance, and in this case, it's going to be 0.2 meters. And now we need to take the moment from the other part of the cable, the one at point A with angle phi, and we're going to use the sine function again. again, we're subtracting because it would cause a negative moment. And so we're going to do t times sine of 22.619 degrees. And then we have to multiply it by that distance. It's going to be 0.36 meters. And then if we do a little bit of some rearranging, we multiply this out. These are like terms, and so we're going to be able to add the two t's. We're going to get 33.6 is equal to 0.258 t. And then if we divide by 2.58 on both sides, we're going to get roughly t equals 130 newtons. It's like 129.9 or something like that. So we'll just call it 130. And so that gives us t. That kind of unlocks the rest of the problem for us, right? That was part A. We're done with it. And so we're going to move on to part B and find the reaction at C. And to do so, we're going to have to do the sum of the forces in both the y and the x. We're going to start with the y though. So we have the sum of the forces in the y. Again, this is statics, and so we're going to say equals 0 because nothing's moving. There's no net force on this member. And then we're going to start with the tension from that cable. And so we're going to say T times the sine of 36.8 plus the T times the sine of 22.619 because that's point A and point B. And then we're going to minus 120. And then when we drew our free body diagram, we didn't remember to write it. But we have a vertical force at point C in the y. Then we have a horizontal one, force at C in the x. And this is the one that we're focusing on right now. We're going to say plus the force at C in the y direction. So if we simplify this, we multiply all this out, we're going to get 77.87 plus 49.998 minus 120 plus F at C in the y direction. That'll equal 0. If we move these three parts to the other side, we're going to get F at C in the y direction equals minus 7.87 newtons. And now if you don't know what this minus sign means, let's take a look back at our free body diagram. We initially guessed this force going upward in the y direction, but because it's negative as we saw over here, that means that this guess was inaccurate and that it actually faces downward in reality, okay? All right, so that's the y direction done. Now we're going to take the sum of the forces in the x direction as well. And so we're going to say sum of the forces in the x equals 0, again, because it's statics. And then now we're going to use the cosine function when we're looking at the cable. So we're going to say t cosine of 36.8 plus t cosine 22.619 minus F at C in the X. This time we made that negative because we guessed it over here to be in the negative direction. If we would have guessed it this way, we would have used a positive sign. But again, if we do a little bit of rearranging, we say F at C in the X direction equals the sum of these after we multiply it out, and we apply 130 to equal T. We get the value of 224.09, which is just about equal to 224 newtons. And that's how you do this problem start to finish.